know that different methods using different criteria have different bias and different problems. We also see some computer simulation data, and to see, well, if we add more data, of course it will be better. And but since our time and money is limited, and sometimes we have to decide, and should we add more taxa or should we add more sequences, I mean the character. And so here are some of the concerns. If you want to add more taxa, you might need to go to the field to collect more data yourself. And if you want to add more characters, which means that you probably need to sequence more, it also costs some money. So for example, you got a funding to sequence 10 KB, which way would be better? So should we use the 4 taxa and additional 2.5 KB, or 10 more taxa with 1 KB each, or maybe 40 taxa with 0.25 KB each? So you need to have some evaluations and which way could be better, and sometimes very difficult to add more taxa, and sometimes it depends on the organism you are working with. If it's very hard to get some more taxa, then, well, you have no choice but to just sequence more. But sometimes it's very hard to find additional markers when you are performing phylogenetic analysis. If you want to add some more markers, you have to evaluate and spend even more time to it. And maybe they'll be easier if you have some taxa at hand, and you can add more taxa instead. So of course, the major concern is to break down the long branch attraction, which is one of the major problems maximum parsimony or neighbor joining, those kind of method will likely face. So how to break down long branch will be the central problem, or the first thing we want to do. But will aiding taxa or aiding sequence, which one would be better to break down the long branches? And that's a lot of studies has been done to evaluate the effect. And there are some simulation data I'm going to show you, and these are the settings for the simulation data. And it says transversion versus transition 2 and the others. And here are the approaches. So we basically start with 4 taxon tree and with 2 long branches right here. And we hope to break down the branch, and after we break down and we got the new data matches, and we want to see if we still can reconstruct the original correct phylogenies. So these are the measurements. We want to see what is the proportion of the trees eventually got to still have the original 4 taxon relationship. And also we want to know the proportion of trees are completely correct, and what is the proportion of the branches to the tree. So these are the simulation data, and here are the 4 different data sets with increases of the character. So start with 1,000 characters, 10,000, 40,000, and 80,000. And the x-axis is the number of taxa we add. So we want to know the performance, and the measurement is the proportion of the correct trees. Y-axis is the proportion of the trees is correct. So 1.0 means that is totally correct. So as we are not so surprised, with 1,000 character, even if you add a lot of taxa, it didn't really resolve the phylogenies, and the proportion of the correct tree is really low. But over 10,000 characters, we'll see when we add more taxa, usually you will get a better performance to get a higher proportion of the correct tree. And but in many cases, it will reach a plateau. And again, because you are adding a lot of taxa, it's basically kind of dilute the effect of the variations inside your data sets. And so it's just 10,000 characters, but 30 taxa will basically dilute the effect. But once you get to a very high number of the characters, the sequences length, for example, so it's very obviously, once you increase the taxa, you'll get a pretty good performance. for getting the right tree. And in this sense, it's very nice to add taxa than the characters, since the payoff you can see, well, of course, it depends on which part of the taxa you are adding. But to sequence a lot of the characters seems to have a little effect from here to here to here. So once you get to a certain point, it's not necessary to add more sequences, the characters in this sense. But it will definitely help on taxa problem. And here is the proportion of the correct trees, and based on the same performance we plotted, and we just compare the 10,000 characters and with a lot more characters. Of course, with the same number of taxa, adding character is still very good. Still have a very high performance compared to the less characters. So basically, they both help. And the other thing we want to know is what if we use the computer simulation a little bit differently? And if we set up the computer simulation to let the branch happen in very early stage or in a very late stage, and you will create some problem. The breakpoint of the long branch will be a little bit different, and we want to see if this will change the performance. And basically, no, there's no differences between those two approaches. As long as you can break down some long branch, it doesn't really matter it happens where. So, which means that sometimes we are concerned that if we want to add one more taxa, should it be a little bit or very closely related to this one, or you should find something at the bottom of the tree. And based on the simulation data, it doesn't really matter that much. But in reality, of course, it's a different story. This is the simulation data. They also compare the performance of maximum likelihood and maximum parsimony. And again, maximum likelihood outperform parsimony method a lot when we add the taxa. So there are some studies already show that if the trees has a lot of taxa in it, you will likely to contain the inconsistent branches. But some people have different opinion, like David Hillis. He will say any tree with a large number of taxa will outperform any trees with less taxa. There are many studies, the real data studies supporting this thinking, and we'll see probably in this example. And this is a tree David Hillis demonstrated that this, I believe, is angiosperm phylogeny. And it has a lot of long branches along the tree. And he did quite a lot of different kind of approach to eliminate the long branches, including elimination of some of the taxa, and or adding some taxa to break down the long branch. And also, he increased the evolutionary rate, everything, to 10-fold. So the evolutionary rate become really high, and it's almost unalienable. But the tree is still accurately constructed with just a few thousand nucleotides. So that means that even though, well, it's based on simulation data, but the data is kind of messy. The information is still there, and that's why we hope so anyway in the real world. So it gives us a kind of confidence that as long as the information is correct and you have a lot of taxa to break down the long branches, you will likely get a correct tree eventually. But this is just some theoretical concern. So here are the performance for the actual divergence and also the 10 times higher rate of divergence, and to see the performance of these two setting. And again, they didn't change much, and it even performed a little bit better for the 10 times divergence data. And even though the evolutionary rate is really high, but basically it will provide more informative sites as well. So I think that's the reason it's like that.